I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me for this video where we are looking at the use of differentials to do approximations. It's a fun derivative application concept we're looking at here. If you consider y is equal to your function f of x, and we know this from precalculus, y is always equal to f of x. Dx is the differential of that variable x. By this relation, dx is equal to change in x, which is your incremental change in x. Looking right here, your dy, the dy represents the differential of y, because here we're looking at differentials for use of approximations. The differential of y by the relation dy is equal to the derivative of x dx. What I have down over here is that the differential of your independent variable, which is normally your x, is equal to the increment, the change in that variable. And you know this to be the case, and you're seeing it right here. It is rather represented by this expression: the differential of a certain variable is equal to the increment of that variable. If the difference between these negligible or very small, then the use of this type of concept for approximations comes out good. If the difference between your differential and your increment is very vast and large, then these approximations are not good at all. So you have to keep that in mind. Look right over here, the dy, the differential of y is equal to that, the derivative in dx. How do you get that? Look over here, if y is equal to the function f of x, you do the derivative dy or dx is equal to the derivative of that function, which you represent as this, f prime x. You push the dx onto the other side, it multiplies, and you're looking here at this representation come out. The differential of y is equal to f prime x, the derivative of x dx. And that's exactly how it comes about. We will be looking here at 3 examples using differentials for approximations, and it's not a hard concept, but it's fun. Let's look over here at our first example, the cube root of 124. How can we use differentials to approximate it? I'm looking at something which is y is equal to this, a certain function y is equal to x to the power of 1 over 3. That's what I have. Let's bring in our differential concept. If I do dy over dx, I'm doing the derivative of this using the power rule. I have 1 over 3 x to the power of minus 2 over 3. And I'm looking at it, I have 1 over 3 x to the power of 2 over 3. I push the dx onto the other side. I'll have dx over 3 x to the power of 2 over 3. And that's equal to dy. And we've determined this, and it's correct. After having determined this out, think of this relationship which I introduced you to at the very beginning. Dx, your differential, should equal to delta x. What is our delta x? What is our differential? We can easily look at it. My question here is a cube root of 124. I know there's such a thing as cube root of 125, which is a perfect 5. This right here is a certain x value. This here is another x value, because these are functions. The function input gives you a certain output, which here is 5, which here will be something we have to determine. What is the change from here to here? What is my delta x? You're looking backward, it's minus 1. I know my dx here is equal to minus 1. I've determined my differential. My differential is very much close to delta x. The incremental difference is small. My dx is equal to minus 1. I'll bring that right over here. I will erase this because you've seen the difference between these two. I have dx over here coming to be minus 1. My dy is equal to minus 1 over 3x. What's x going to be? Well, let's assume x here is going to be 125, which I was showing you momentarily previously, which is equal to 5 cubed. Now this is what my x is coming into here, is 125 to the power of 2 over 3, which you can easily calculate without even a calculator. I have 125, which is 5 cubed, to the power of 2 over 3. These cancel out. I have here a 25. I'm looking here at minus 1 divided by 3 times 25, which is a minus 1 over 75. That is it, minus 1 over 75. My end equation will be, in terms of the approximation, is your y plus your dy. Dy is equal to everything from this computation, which is right over here. What's my y going to be? My y is going to be the cube root of this. As I'm determining a certain function, cube root of 124 is equal to y. A close approximation is y is equal to cube root of 125, and we know that to be a solid 5. And that right there is my y value, y plus my dy value, which is a minus 1 over 75. Do this computation. 5 minus 1 over 75 will give you the close end result for that. We'll do 5 minus 1 divided by 75. I have here 4.9866, and that's our end result, and it will be good by means of differential approximation. 4.98666. Here is our end result, and it will be good. How did we do this? By means of differentials, because the dx was equal to delta x, the incremental difference was negligibly small. Here we determined it to be a -1. Very good. This here is our end result. Let's look here at another question. Our question number 2 is this: y is equal to 4th root of 17. I'm looking over here at y is equal to x to the power 1 over 4. A certain output of this is what I'm going to determine by means of approximations using differentials. The derivative dy over dx using the power rule is the derivative of this 1 over 4 x to the power of, you'll do your power rule x to the n. The derivative is equal to n x to the power of n minus 1. What's 1 over 4 minus 1? It's a minus 3 over 4. When you rewrite it, you have here 1 over 4 x to the power of 3 over 4. This is what I have. Now let's determine dy. This is dy over dx. When I push the dx on the other side, I have here the dx coming. This is equal to dy. This right here, relationship dy is equal to dx divided by 4 x to the power of 3 over 4. Now I want to determine my dx, my differential with x. I know there's something very close to this. The 4th root of 17 should be equal to or closely 4th root of 16. This is what I have. Here's a certain x value and here's another x value. When I'm looking from this new x value backwards, I have a delta x which is equal to a plus 1 because I'm 1 unit away, but this is plus 1. I know my dx is equal to my delta x by that relationship I've introduced you to already. This right here is equal to a 1 and it's easy and it helps us out. We know dx here is equal to 1. We don't even need to write it because it's meaningless to put a 1 over here. We already have a 1 here. Anyhow, we know this 1 is coming right over here. Let's think of our approximation. I'm looking here at 4th root of 16, which we know to be 2. This is what I have. This right here will be my y value. Now I'm looking at y plus dy. And what do I have? I have y, which is 2. I need to determine dy, which is this. And I know this right here is what's going to come right over here. I'm looking over here at dy is equal to positive 1 because my dx is positive 1 over 4x, which is 16 to the power of 3 over 4. You don't even need to use a calculator. You know 16 is 2 to the power of 4 to the power of 3 over 4. These cancel out. I have a 8. I'll have a 1 over 4 times 8, which is a 1 over 32. This right here is my dy. My differential with respect to y is 1 over 32 and it's done. This right here will be your end result. You can bring your calculator and calculate that. It will be correct. And let's bring it in. Keep in mind in the previous question we had a delta x and a differential equal to a -1. Here we have a positive 1. So these type of changes can happen, but the difference is negligibly small. It's not like a positive 10. It's a positive 1. It's negligibly small. 2 plus 1 divided by 32. This is your answer, 2.03125. It should be equal to this, 2.03125. Not exactly equal to, but very close that you would be satisfied with the result. Bring in your 17 and the 4th root. I have here 2.0305. I'm deferring by this digit, 3rd digit onwards, but again, in this particular case, the positive 1 difference or increment is still a little larger than preferable, hence the approximation is not exact, but it's very good. So this right here is question number 2. Let's look at one more question and we are done. We close out with this one, the 5th root of 1020. We can use differential to approximate this, and how we do it. We're looking at a certain function which is a 5th root. Y is equal to x to the power of 1 over 5, the 5th root. Then obviously you have to do the derivative of this. The derivative with respect to the variables you see, dy or dx is equal to the derivative using the power rule, 1 over 5 x to the power of -4 over 5, because this right here is always a -1 using your power rule. 1 over 5 minus 1 is a -4 over 5. You'll have over here 1 over 5 x to the power of 4 over 5. When you push the dx onto the other side, it can multiply. You're having here a dx, which I'm going to bring right here. Dy over dx is equal to this. Push the dx, you have dx over that. This right here is equal to my dy, and this computation over here is good. Now what we have to do is start determining what x is, what dx is. I'm thinking of a certain item which is close to that, and if I do 5th root of 1020, it should be relatively close to the 5th root of 1024. Why am I picking 1024? Because 4 to the power of 5 is equal to 1024. This right here is my y value. This right here is my x value, which will come right over here. what is my delta x? When I'm looking backwards in this direction, here's my x value, here's my other x value. My delta x looking from here is a minus 4. I'm looking back minus 4, which should be equal to my dx. So now my dx is equal to minus 4. When we come back here into this equation, we have dy is equal to dx, which is a minus 4. Remember, from 1024, if you minus 4, you get 1020. 5 times x. What's my x value? Right here, 1024. 1024 to the power of 4 over 5. These type of numbers you can calculate without a calculator because the laws of exponents come into play and they are easy to handle. Think of this computation. 1024 is 4 to the power of 5 to the power of 4 over 5. These denominator 5s cancel. You have 4 to the power of 4. Now obviously you can bring out the calculator and let's do it. 4 exponent 4 is a 256 times 5. This is my denominator value. My dy is equal to, without simplifying the values, minus 4 divided by 1280. This is what I have and we'll keep at that. Nothing wrong with it. Now let's look at our final relationship, which you have seen now. Y plus dy gives you your end result of your approximation. My y here is what? The base here, 4. My dy is the end result of this, minus 4 over 1280. Do this computation. You can do it on your calculator and we'll bring out our approximated value. 4 minus 4 divided by 1280. My end result here is 3.996875. Let's bring it out and let's write it out. 3.996875. It should not be exactly the same as this, but it will be very close to it. Let's look at the value. 1020, the fifth root, I have here 3.996870. Here I am getting a 7.5, but the actual value is 70, so we're differing. In terms of our approximation, we're off only by this digit right here, and it's excellent. After having done these 3 questions, it seems like there's a good trend which develops. The differential approximation is fairly close. If 2 items come into play, it's a tug of war how they relate with each other. One is this. Your delta x, which is equal to dx, your increment should be small, and we've seen that. And this base value also matters. If this increment is small, but the base value is small, then you could have an approximation which is not good. If this increment is small but the base value is very large, as in this question right here, then the approximation is very good, as you saw. Here our increment was a minus 4. We're looking here at only the 4. We have an incremental difference here of a 4, but we have a very large base value and our approximation is very good. Think of the question you saw previously where we were looking at the 4th root of 17. In that we had a delta x which was equal to dx of a positive 1. We're looking here only at the 1 value, but our base value here was a 17. We had a small base value, but we had a small increment, but our approximation was not too good. So it's a tug of war between this value, is it too large or very large in the face of a very good negligible difference with delta x and dx, in which case your approximation will be very good. Keep that in mind. That's it for this video. Thank you.